Okay, so extending beyond what we covered last lecture, talking about linear optimization models in Excel. So we looked at specifically three sort of flavors or three kinds of linear optimization problems. Allocation models, covering models, and blending models. Okay, not every linear optimization problem obviously can fit into those three forms, and those are really just special cases. In the case of allocation models, you're maximizing your objective subject to less than or equal to constraints only. Okay, covering models are just the exact opposite, and blending models, like we just talked about a few minutes ago for assignment 4, is one where you have constraint values based on the ratio of your decision variables, or the ratio of two things calculated from your decision variables, in which case that's a nonlinear function, but you can algebraically manipulate it to be linear if you need to or want to. Okay? Certainly, even in that example we did from homework or assignment 4, the blending model involved both a less than or equal to constraint and a greater than or equal to constraint, right? So it's not always the case that all your constraints will be one type or the other. You might have some of both, okay? So certainly those would be more advanced or at least different linear optimization problems. Tonight we'll talk about a couple more types of linear optimization problems, okay? We'll start with network models, which again are just a subset of all possible linear optimization models. They follow a fairly standard form, and we'll see what that looks like. But like all linear optimization models, you're just going to have decision variables, an objective to optimize, and constraint functions. Okay, so everything always boils down to those three components. Okay. These different styles or types of models, it isn't important to memorize them or necessarily even understand them. They're just helping us build and learn how to build linear optimization models. Okay, that's all we're using them to do. And there's classes of models that look alike, which is why we give them names. But all linear optimization models are solvable the same way, with the same tools, with the same techniques. Okay. And so there's not really anything special about one type of model over the other. We're just taking sort of a tour, as it were, through the different types, just seeing what they look like and how they all relate together, how they're all linear optimization models. All right, so we'll do that, and then we'll close talking about integer and binary models, which are another special class of linear optimization in which your decision variables are limited to whole numbers, integers, or binary numbers. Okay? All right. So linear network optimization. Network optimization problems are described as systems of flows where you have something like a source and a destination, and you want to figure out how much of something should flow or should move between the source and the destination. Generally, we'll describe things like costs that say for every item or product or thing that flows from the source to the destination, it has to pay some cost to get there. But we have need at the destination, so we need some minimal amount, right? So we have to figure out, for example, from multiple sources, how to get enough of something to a common destination from those sources in order to, say, minimize cost of that movement or of that flow from source to destination. Generally speaking, we can represent or sort of visualize these kinds of network optimization models using a diagramming technique with just circles and lines, or circles and arcs, that I'll show here in just a minute. Okay, so that just helps us visualize how the problem works. We'll translate that visualization into the model in Excel. Okay, so let's see how that works. The first example we'll take is a very simple one involving just transportation. We have sources, we have destinations. We need to transport something from the sources to the destinations, and minimize the cost of doing so. Okay, so here's an example we'll take. An electronics company planning next week's shipments from its 3 manufacturing plants to the 4 distribution warehouses. Okay, so we have 3 sources where things are made, and we need to ship the stuff that's made at those sources to 4 distinct destinations. Okay, each plant has a potential, and we're seeking to minimize the cost, right? So there's a cost to ship from plant 1 to distribution center 1, from plant 1 to distribution center 2, and so on. Every pair of source destination has a cost. Furthermore, each plant has a capacity, so each plant makes only a certain number of things. It has to ship all of them out, okay, probably. Can't ship more than what it has, certainly, but it could ship to any one or more of the destinations. And then each warehouse has a requirement, a minimum, that we want to ship to it. There are 12 possible shipping routes for each route. The unit cost is known, or the shipping cost is known, and looks something like this. Okay, so this is just a simple table describing what we have. So we have our 3 plants in terms of 3 different cities they're located in: Minneapolis, Pittsburgh, and Tucson. Those 3 plants, if you look on the right-hand side of the table, each have a capacity. So Minneapolis produces 9,000 units that it can ship to any one or more of our 4 warehouses. Pittsburgh has a capacity of 12,000, and so forth. The unit cost for each thing shipped is given by the intersection of 1 row, a plant, and 1 column, warehouse. So to get a unit from Minneapolis to Atlanta costs 60 cents. To get 10 units would cost 10 times that, or $6, and so forth. To get something from Pittsburgh to Boston costs 30 cents, okay, for each unit. And then each warehouse listed here at the bottom, so Atlanta needs 7,500 units, Boston 8,500, Chicago 9,500, and Denver 8,000, okay? So we have 3 sources, 12 shipping routes to go from those 3 sources to 4 distinct destinations. Each source has a capacity, a maximum amount it can ship out. Each destination has a requirement, the number it wants shipped to it, cumulatively from all the sources. Okay, so we can visualize this with a diagram. Looks something like this. I'm just going to use circles because they're easy to draw. Each one representing one of our plants: Minneapolis, Pittsburgh, and Tucson. Okay, and then we have 4 distinct warehouses that we want shipped to: Atlanta, Boston, Chicago, Denver. Okay. And the reason we call these flows is you could imagine Minneapolis, wherever it gets it from, or however it makes it, has a certain amount of flow into it, 9,000, and that has to equal the number that flows out, whether it's going to 1, 2, 3, or all 4 of those destinations. Okay? And similarly, Pittsburgh has a sort of inflow limit, that is, only so much can really come out of Pittsburgh, okay, and that's known to be 12,000, and for Tucson it's known to be 13,000, okay, and likewise we want what comes into Atlanta from any one or more of the 3 sources to add up to 7,500, Boston 8,500, Chicago 9,500, and Denver 8,000. Okay. So the question is, where should Minneapolis send its 9,000 units? Should it send them all to one destination, or half to one, half to another, or some other split, maybe a little bit to all 4? And similarly for Pittsburgh, so Pittsburgh's going to send, and Tucson's going to send, right? So there's technically 12 decision variables of things we need to decide. We need to decide for each pair of source and destination how much product should be shipped on that route, how much flow should come from that source to that destination. Okay? So 12 decisions to make, limited by, so these 4 decision variables of how much flows to each warehouse from Minneapolis must sum to less than or equal to 9,000. Right? Minneapolis can't ship any more than 9,000 because that's all it has. Similarly for Pittsburgh and Tucson, they're limited. Likewise, the 3 incoming arrows here to Atlanta, one from Minneapolis, one from Pittsburgh, one from Tucson, those 3 decision variables must sum to 7,500. Okay? Because it needs that much. Right? We want to make sure to meet that need, and so forth for Boston, Chicago, and Denver. Okay? 12 decision variables. Okay? 3 constraints on capacities, 4 constraints on requirements. Okay? And then in the end, right, we want to know how much does it cost. Right? For every unit shipped from Minneapolis to Atlanta, that costs 60 cents. For every unit shipped from Minneapolis to Chicago, that only costs 22 cents. Right? So obviously there's an optimal selection of values, what to ship where, that will minimize the objective of cost. Okay? So cost will be a function of all 12 decision variables. Linear function. Just these 12 numbers multiplied by each decision variable, one by one, added up. 3 constraints will be a constraint on 4 of the decision variables each. Another 4 constraints will be a constraint on 3 decision variables each. Right? Simple enough. So, let's look at how we can do this in Excel. I'm going to copy all this, take it to Excel, paste it in. Worked remarkably well. Okay, so we have our plants, we have our warehouses, we have limits on capacity, we have limits on requirements. Okay, I'm actually going to take that just as is, paste it up here. Okay, and compute my decision variables in a block, similar block of 12 cells in Excel, 3 rows, 4 columns. Okay. And my objective will be, so let's just make up some numbers to start with. Maybe it'd be easiest to make up, I don't know, some zeros. Maybe this is 1,000. Maybe this is 1,000. 2,000, 0, 0. Oh, we need a little bit here. Maybe 3,000, 2,000, 1,000, 2,000. All right. So if that's the number of units we're going to ship, so these same table of cells will correspond to the same table up here. So each row is a plant, Minneapolis, Pittsburgh, Tucson, and each column is a warehouse, Atlanta, Boston, Chicago, Denver. So this says I'm going to ship 0 units from Minneapolis to Atlanta. I'm going to ship 1,000 units from Minneapolis to Denver. Right? So this block of cells form our decision variables of how much to ship from the plant represented in that row to the warehouse represented in that column. Okay. Now, our decision, or our objective function can still nicely use the sum product function, which it turns out doesn't just work with rows, it works with rows and columns as well. So if I select the sum product of all 12 of these cells here, multiplied by one by the corresponding cell in these 12 here, it'll sum all that up for me and tell me how much that costs. Okay, so make that a currency, and it turns out that this particular set of decisions would cost 5,830. Okay. However, we need more than just the decision or the objective function. We need a set of constraints, okay, which we can nicely compute, again in a tabular fashion. If I sum each row of my decision variables, the sum of each row tells me how much product, how many units are being shipped out of the plant represented by that row. So Minneapolis obviously ships 100 or 1,000 to Denver, 0 everywhere else, so it's shipping 1,000 units out in total. Pittsburgh is shipping 1,000 to Atlanta, 2,000 to Boston, that's a total of 3,000, and so forth. Those three values we're going to constrain to be less than or equal to the three capacities we see above. Okay? So obviously this has to sum, this row of decision variables summed up must be just simply limited to be less than or equal to 9,000. Same thing for the columns. We can sum up each column of decision variables, and we're going to constrain each one of those to be greater than or equal to, right, the requirement. So we need to at least that much coming into the warehouses, but no more than these sums on rows coming out of the plants. Okay? So, like always before, I'm going to select our decision variables, all 12 of them, mark them as such for Analytics Solver platform. I'm going to take the cell where we computed our objective function, mark that as the objective. In this case, we're minimizing this cost. Okay. And then the 7 constraints, I'll input as 2 sets. First, constraining each plant output to be less than or equal to the corresponding capacity. So cells F9 through F11 must be less than or equal to the corresponding cell from F3 to F5. And the sums of the columns will constrain to be, now this is where I'm going to use greater than or equal to. It would never make sense to ship more than is required because that costs more, right? So we'll see that it's always going to choose values equal to, not greater than. But without any loss of meaning, we can just say greater than or equal to, like we do with a lot of our other constraints. Okay? And as always, we want to ask the question about implicit decisions. Does it make sense that we would limit these to only be 0 and positive? And the answer is yes. We certainly wouldn't make sense to ship negative numbers of units. And optimally, right, we could choose to do that. That would certainly help lower and minimize cost. In fact, you can ship negative, 1 billion units for a lot of negative cost. So the model would try to do that if we would let it. So we better tell it to assume non-negative for the decision variables. Okay? And then finally, we'll run the model. So in this case, optimal decisions, right? We can describe the pattern, go through one by one of the 12 decision variables and say how much is being shipped from each plant to each warehouse. Certainly, we should have met each requirement, which we do. Okay, so Atlanta got its 7,500, Boston its 8,500, Chicago its 9,500, and Denver its 8,000. In terms of capacities, it turns out we didn't ship all of the product from one of our plants, right? Which just means that we technically made and had a capacity for more than the requirement at each warehouse, right? So for whatever reason, the company, right, whether on purpose or accident, has more capacity than necessity, requirement. So we actually chose to make only 12,500 units in Tucson, or only ship that much, even though we could have shipped or could have made 13,000 units. Okay, that's okay, right? That certainly helped us minimize cost by only meeting the requirements subject to not violating the capacities, but we didn't necessarily have to use all of the capacity. I'm going to come back here to the board. Let's visualize this solution using this same diagram. Okay. So we know Minneapolis had 9,000 units to ship. It turns out it shipped all of its 9,000 units, right, to Chicago. So we can draw a line, label it, and easily see Minneapolis shipped all of its product to Chicago. So I'll just not even draw lines to the others, right? No point in drawing a line, labeling it with 0. Okay. So Minneapolis's product all went to Chicago. What about Pittsburgh? Well, Pittsburgh split what it made, shipping to both Atlanta and Boston. 3,500 units to Atlanta, 8,500 units to Boston. Okay. And you can see that 8,500 units from Pittsburgh to Boston meets all of Boston's demand. So Boston won't need any more. It didn't need any from Minneapolis. It won't need any from Tucson. It got all that it needed from Pittsburgh. Atlanta only got part of what it needed, right, from Pittsburgh, right? Because Pittsburgh only had so much it could send, right? So 3,500 plus 8,500 is 12,000. That was the capacity limit of Pittsburgh. So Pittsburgh sent all that Boston needed to Boston, and the rest of what it had to Atlanta, which means, as you can see, Tucson had to send some to Atlanta to meet Atlanta's demand. So it shipped 4,000 units to Atlanta. It had to ship a little bit to Chicago, right? Chicago needed 9,500. It got 9,000 of it from Minneapolis, all that Minneapolis had. So Tucson sort of had to make up the shortage in both Atlanta and Chicago and then meet Denver's demand, right, completely by itself. Okay. So that was the optimal solution. Okay. So again, you can visualize this with this kind of a diagram. I would not draw arrows for a 0, just to keep from cluttering the diagram. But this helps you visualize, right, what that solution told us. You easily see patterns, like are there any sources that ship solely to one place? Yes, Minneapolis ships solely to Chicago. From there you can see, well, Chicago needed more than it could get from Minneapolis, so it would have had to get some from at least one other place. Right? Likewise, you can say, are there any other destinations that get all of their demand met by a single source? Yes, Boston gets everything it needs from one place, Pittsburgh. Likewise, Denver gets all it needs from one place, Tucson. Okay. Obviously, this minimized cost, because that's what we told it to do. Let's look and describe why that's the case. So just looking up there, the minimum cost path, right, in all of that model was from Minneapolis to Chicago. That's the cheapest route to send anything on, from any source to any destination, for 22 cents. So it kind of makes sense why Minneapolis sent everything it could to Chicago. Chicago needed more than that, but still, it was cheapest to meet as much of the Chicago demand as we possibly could from Minneapolis. That's the cheapest route, right, in all the model. Next cheapest route, just looking through, looks like Pittsburgh to Chicago. Right? So the next cheapest thing to do would have been to ship at least the rest of what Chicago needed from Pittsburgh. However, it didn't do that. Right? So there was a small amount needed in Chicago, 500 units still. It would have been cheaper to get them from Pittsburgh. It's much more expensive, it turns out, to get them from Tucson. And yet, the optimal solution chose to get it from Tucson. Right? Because, well, why? Let me ask. Why, if it's cheaper to get 500 units to Chicago from Pittsburgh, did the optimal solution get 500 units to Chicago from Tucson?
Because the difference in price to get it from Tucson to Pittsburgh or to Atlanta or Boston is much higher than the difference in cost between getting it from Pittsburgh to there versus Chicago.
Okay. So you said the difference in getting from Pittsburgh to Chicago, which was 55 cents versus 28 cents, right? Which should be something like a 27 cents difference, right? So we chose to pay a 27 cent higher rate, okay? For what trade-off? Well, there's likely a couple trade-offs. One of them could have been the difference in how much it would have cost to ship from Pittsburgh to, say, Boston, as opposed to Tucson to Boston, right? Because we chose to ship Pittsburgh product to both Boston and Atlanta, not Chicago, okay? Obviously, Minneapolis, we already used everything it had because it was the very cheapest thing we could have done. That made sense. How much did it cost to ship from Pittsburgh to Atlanta? Well, Pittsburgh to Atlanta cost 36 cents. Tucson to Atlanta cost 65 cents, right? That's a 29 cent difference, right? So obviously, the 29 cent higher, right? We wanted to ship from Pittsburgh to Atlanta at least as much as we could, as opposed to Tucson to Atlanta, even though we had to in the end do a little bit of both, right? Likewise, Pittsburgh to Boston. Pittsburgh to Boston costs 30 cents. Tucson sending to Boston costs 68 cents. That's a 38 cent difference. So clearly, if we had to choose between some options of a 27 cent savings, a 29 cent savings, and a 38 cent savings, we'd want to save 38 cents, right? Which means, again, that's the difference of shipping Pittsburgh to Boston versus Tucson to Boston. We save 38 cents by shipping it from Pittsburgh, not Tucson, which is why, presumably, Pittsburgh ships all that Boston needs so that none of it has to come from Tucson. That's more than Pittsburgh has, so it still has more to send. Well, obviously, Pittsburgh should send to Atlanta next for a 29 cent savings over Tucson, as opposed to Pittsburgh shipping to Chicago, which is only a 20 cent savings, as opposed to Tucson. Right? So that's why Pittsburgh did not send to Chicago, despite that being the second least costly path. Right? So with a little bit of analysis, we can help explain that. I'm not going to ask you to do that on the assignment, by the way. Okay? So you don't have to worry if you didn't follow all of that. You're okay. Hopefully, if you did follow it, it just helps you understand why the pattern, particularly in this case, looked like what it did. Yeah.
So let's say, not to go off on a tangent, but just so we do have a surplus of 500 units or whatever we're talking about sitting in Tucson.
Yes.
And while we want to minimize costs, I'm guessing in a real-world scenario, we'd also want to maximize profit. We wouldn't want the surplus building up or to have the factory performing below what its optimal capability is.
Sure.
So would we do some kind of optimization sensitivity analysis to figure out which of our routes we should try to negotiate lower rates on in order to try to ensure that that's no longer a binding constraint? Or that becomes a binding constraint only?
So let me try to repeat the question to make sure I understood it, because it sounded like there may have been two parts. One was the observation that we didn't ship everything Tucson has as a capacity, although in a real-world sense, you wouldn't want to just leave product sitting somewhere. Presumably, you'd ship it somewhere because you can sell it for profit. Certainly, this model didn't take that into account. In a real-world scenario, you'd be concerned with minimizing this cost subject to maximizing profits, because presumably you can sell for a profit at each one of these places. Maybe the same profit, maybe different, right? So that's another model, maybe for a more complex day. That's why we didn't have to ship everything out of Tucson, okay? Now, your next question sounded like it would have been, or something to the effect of, using optimization sensitivity, would it make sense to, say, find out which route, right, is the one of a cost that we should try hardest to minimize, negotiating better rates or something, in order to get better solutions? That's certainly possible. That's a little bit more advanced of a form of optimization sensitivity than we are going to learn in this class, because it would involve optimizing all 12 parameters, the costs, sort of at the same time, or figuring out which one is the one to optimize optimally, for lack of a better term. Optimization sensitivity in this class, we're going to focus on one parameter only, at a time anyway, for simplicity's sake. It's not the only way to do it, but yeah. That's not a bad idea.
Well,
We couldn't do it here, but we won't learn how to do it.
doing it here. I mean,
Right.
Not looking to add to our homework or exams.
Sure.
Just curious as to, like, once this goes to, like, a real world.
Mm-hmm.
And
Yeah. So in the real world, likely this kind of a problem isn't going to be nearly this simple. There'll be profits involved. There'll be other things involved, some of which we'll try to get to later tonight, a little more complex of models. And certainly if you were going to try to do some optimization sensitivity analysis, you'd want to do it on maybe multiple parameters at a time and try to figure out very complex questions, such as which route should we negotiate a lower rate for, right? Assuming you could get maybe a 10% discount, which route would you want to get a 10% discount on to better optimize the optimal pattern, right? Or maybe it's 10 cents. Right? Maybe you think you can get a 10-cent discount on any one route cost. Which one would you want to get it on for the best, in this case, lowest cost? Yeah, that's a great question in the real world.
So,
Yes.
to turn that question around, do people like, like for instance, cloud computing providers, or even just, normal, like UPS or FedEx, do they do a reverse version of this or something to figure out how to come up with their tiered pricing models?
Yeah, so the question is, does a company like a cloud computing company or like UPS, which does literally shipments like this, do they sort of do the reverse of this to figure out their pricing models? Probably something to that effect, yeah. They probably compute, well, so like a UPS, they have fixed costs. They know, it costs gas, it costs a driver you have to pay to go from one place to another. They would use that information, maybe with something like a model like this, to figure out how much should we charge, right? Now, that would assume, well, the more you charge, the less people are likely to use that route or use your services. So somehow they have to model that and kind of come up with an idea of what's the maximum amount we can charge to get more profit before we really start diminishing our service, the people who will use our service, which reduces profit. Right? So somewhere there's a balance. If you had an idea of how that looked like, you can create a model for it in Excel or something else and answer that question. Yeah. Okay. That's the transportation network model. So again, 3 sources, 4 destinations, makes for 12 options of shipping, 12 decision variables. In this case, roughly half of those decision variables we left 0. That is, we didn't use all of the 12 routes. We only used about 6 of them, in fact, so about half. That's not always going to work out that way. Sometimes you'll use fewer, sometimes you use more, right? All in all, in this case, we met 2 of the demands from 1 source only, and the other 2 demands from 2 sources. Okay, it's just the way it happened to work out. Now, we could use optimization sensitivity, and let's describe what that would look like to answer a question such as, let's say, so Pittsburgh sends all of its product to Boston. We know that right now. One possible question we could ask is, how expensive would that route have to get before we would stop doing that? That is, right now it costs 30 cents a piece. What if it costs 31, 32, 33, right? How high would that cost have to go before Pittsburgh would stop shipping all of its capacity, or not all of it, sorry. How long before Boston would stop receiving all of its demand solely from Pittsburgh? Okay, so let's do some optimization sensitivity. To do that, I'm just going to pick a blank cell. We're going to use the parameters button, making sure to select optimization. So our lower bound will be 30 cents, maybe our upper bound, let's do 60 cents. Not sure where, but probably somewhere in that range things would change. And then let's set cell C4, currently 30 cents, equal to that cell I used for the parameter, G7. I like to do the parameter in a separate cell as opposed to the cell like C4 itself, because it makes it a little more obvious. You could label this cell out here something like Pittsburgh to Boston param, and so you know what you're looking at. You know you're performing some kind of sensitivity analysis. You can even do things like put a border around it and all sorts of stuff. It just makes the model easier to recognize, as opposed to if this formula was directly in this cell, you'd have to know that, right? You can't visually distinguish that without clicking on the cell, as opposed to other cells. Okay, so now it's sort of called out that we're parameterizing this model with something special over here. So then all we have to do is select reports, optimization. There's an option for parameter analysis. The parameter is found in G7. We have our variables. Now, we have 12 variables. I'm only really going to be interested in a couple. Specifically, I'm interested in the variables in column C, because those are the ones that represent where Boston gets its product from. Right now, it gets all of it from Pittsburgh, but we want to know where would it start getting it from if the cost of Pittsburgh to Boston were too high, or high enough. Okay, we might also be concerned about row 10, simply because that's where Pittsburgh is sending. So we might also ask the question, well, if it was too expensive to go from Pittsburgh to Boston, where would Boston get its product from, and where would Pittsburgh send its product to as an alternative? And let's use 31 points because we have a range of 30 cents. So we'll run the optimization. It's going to re-optimize 31 times for all 31 points in that range, and then give us an analysis report. So here in column A, we see here's the cost of going from Pittsburgh to Boston. We know at 30 cents, Pittsburgh sends everything, or as much as it can, to Boston, as much as Boston needs, and it sends the rest of it to Atlanta. Just looking down through here, it looks like finally at 39 cents, from 38 to 39 cents, the optimal pattern changes. No longer does Pittsburgh send all of what Boston needs, although it still sends some of what Boston needs. Instead, it sends to Boston, and Boston further gets the rest of it from Tucson, right? That's cell C10 and C11. Pittsburgh, on the other hand, since it's sending less to Boston, can now send more to Atlanta, right? So if you think back to what we had drawn on the board, the line from Pittsburgh to Boston has reduced. The line from Tucson to Boston now has something other than 0 on it, and the line from Pittsburgh to Atlanta is now larger. So 3 things changed in response to the cost of one route becoming too expensive. Furthermore, at a price of 41 cents, the optimal changes again, and you start shipping to more routes, in effect, change. And up to 60 cents, that pattern holds. Okay. So just to answer the question I originally posed, how expensive does the Pittsburgh to Boston route have to be before the optimal pattern changes? The answer would be 39 cents. At 39 cents, that route becomes so expensive, we don't want to ship as much on it. We want to ship less on that route and more on other routes. Okay. All right, any questions about the sensitivity analysis? right?
So would the correct way to phrase that be somewhere between 38 and up to 39 cents?
Yes. So yeah, the all we know is at 38 cents the old pattern holds. At 39 cents the pattern has changed. Somewhere between 38 and 39 cents is the sort of break-even point. So we don't necessarily know that. We could go back and rerun optimization from 38 to 39 cents with more points in between.
But
Ultimately, right, it'll come down to some very exact value, but that's going to be a fraction of a cent. Probably not that important. If I were to ever ask questions like this, I would just expect you to, say with certain resolution. So in this case, within 1 cent, we know it's somewhere between 38 and 39 cents. That's close enough, right? If I wanted a higher resolution or accuracy or precision, I'd tell you so. I'd say within half of a cent, where does the pattern change, right? All right. Well, let's move on. So that's a network optimization model. There are other kinds of network optimization models. That one we were just talking about shipping things from sources to destinations. There's a special class of optimization or network optimization models that we would call assignment, where we want to effectively assign one source to one destination. Okay, so instead of saying how much something should flow between, you're just deciding which place should it flow from and to, and you're always your capacities and demands are all limited to one. Okay, so here's a good example of that. Let's say you're a swimming coach, right? And you have 4 swimmers, so 4 people on a relay team, and there's 4 different swimming strokes that you need to assign each swimmer to swim in the relay. So obviously each swimmer has to swim one and only one stroke, and every stroke must be swam by one and only one swimmer. That's how relays work, right? It's not a relay if one person does two strokes or 2 parts of the relay and another person does 0, right? So this is a special network. We have 4, if you want to call them sources, that's fine, and 4 destinations, and you basically have to find just 0 and 1, right? Which person is assigned or not assigned to each stroke, right? So each swimmer assigned to 1 stroke, only 1. Each stroke assigned 1 swimmer and only 1 swimmer. So obviously there's more parameters than that. In this case, we need to know how fast does each swimmer swim each of the 4 strokes. Presumably the relay time will be the sum of how fast each person swims their assigned stroke, and we want to minimize that time. We want to construct the relay team such that everybody is swimming a stroke such that we minimize our total time in the swimming pool, right? Total time in the relay. So somebody's fast at something, somebody's the slowest at something, and so forth. We just need to know who should be assigned which stroke. So I'll copy this, take it to Excel, paste it in. So these are the parameters to the model. As before, we'll have our decisions, our decision variables, which will be a table of the same size as before, so a 4x4 grid. And let's just assume we'll assign, well, the names were Todd, Betsy, Lee, and Carly. We'll assign Todd the butterfly, we'll assign Betsy the breaststroke, we'll assign Lee the backstroke, and Carly the freestyle. Okay, without knowing anything better. Okay. We're going to sum each column like we had before. We're going to sum each row like we had before. And in this case, the rows must all sum to 1, but they must all be 1, and the columns must all be 1. That simply just asserts that Todd, Betsy, Lee, and Carly were each assigned only 1 stroke, and that each stroke was assigned only 1 swimmer. So rather than limit those, I'll just type in 1 when we put in the constraints. And then finally we have our objective, which we can use sum product to multiply the times by the decisions. The nice thing is, okay, the decision variables are all going to be 0 or 1, right? So we're either assigning somebody or we're not, okay? We're not going to have to tell the model to do that. It's going to naturally happen, and here's why. Because we're limiting each row to 1 and each column to 1 as a total, it would never make sense to have somebody swim a fraction of one stroke and a different fraction of another stroke, because they're either faster at one or faster at the other. So it would never make sense to sort of split their time. Okay? For example, if Todd can do the butterfly faster than the breaststroke, and Betsy can do the breaststroke faster than the butterfly, you would never want each of them to swim half of each. You'd want Todd doing what he's good at, Betsy what she's good at. Intuitively, that makes sense. Naturally, the way that's going to work out, we won't have to tell the model you can only use 0 and 1. We'll tell it you can only use positive values, non-negative values, so it doesn't try anything weird. But it will naturally only use 1s because every column and row has to sum to 1. Okay? So,
what if somebody had inverse, like let's say one person was twice as fast as one thing as the other, and another person was the exact inverse of that, then wouldn't the model maybe get confused and think that...
Yeah, so the basic question is, well, what if, just as a simple example, what if Todd was equally fast at both strokes and Betsy was equally fast at both strokes? Would it get confused? Turns out it won't, luckily. Because of the way linear optimization works, if you think back to how we did it by hand, you always find, for example, corner points on the solution space, and you basically just go one by one and say which one is the best, right? And if one's just as good as another, that's okay. You would technically, what that would mean is between two corner points, you could go anywhere between the line that connects them, right? Halfway in between, a quarter of the way, 3/4 of the way, they're all the same, right? If they work out to be the same, you would still just pick one. Maybe the first one you came to or the last one you came to, it wouldn't matter if they're equally the same. But because of the way we do it, right, we always pick at least a corner point. We never try any values in between. So we would always either assign Todd the butterfly, Betsy the breaststroke, or vice versa. If it was the same either way, we would always do a 1 for 1 and a 0, or 0 and a 1. We'd never want to do anything in between. Yeah. Okay, so here are our 16 decision variables. These 4 rows are constrained to be technically, again, we could use equal. Maybe we should do that. So we want every row to sum to exactly 1. And we want, that was every column. And we want every row to sum to exactly 1. So we can use equal here. And I'm just typing 1 as the value to constrain it to, as opposed to type in a bunch of 1s somewhere else. And then finally we have our objective cell, which is the total time the relay would take if everybody swam whatever stroke they're assigned and there was no time in between, right? No transition time. And that we want to minimize. And remembering to set assume non-negative to true, otherwise it might try to make somebody swim a negative stroke. And solve. So, found a solution. Everything looks green. And what it found is Todd should swim the backstroke, Betsy the freestyle, Lee the breaststroke, Carly the butterfly. Okay. If you look through, let's say butterfly, who swims the butterfly the fastest? It's Carly. Makes sense why she was assigned that. Well, who swims the breaststroke fastest? Turns out it's Lee. Makes sense why she or he was assigned the breaststroke. Okay. However, Todd is not the fastest swimmer of the backstroke. He's not the slowest, right? But he's not the fastest. But certainly the fastest swimmer of the backstroke being Lee, well, Lee already was assigned the breaststroke. He was better at that. We can't have them swim both strokes, so we couldn't swim the backstroke. Lee couldn't swim the backstroke. Likewise, freestyle, it works out. Betsy was the fastest. She got assigned that, right? Which means poor Todd, who isn't the best at anything, right, gets what's left over, right, effectively, and he's swimming the backstroke. Now, obviously, if Todd was really bad at the backstroke, much worse than everybody else, we'd probably rather him swim something else, right? Turns out he's only 3 seconds slower than the fastest swimmer of the backstroke, right? So we're only 3 seconds worse than we would have been if we'd had Lee swim the backstroke instead of Todd. Whereas if we had Todd swim the breaststroke so that Lee could swim the backstroke, he's 4 seconds slower than Lee at that. Right? So it makes sense why we'd rather him swim the backstroke, not the breaststroke. Okay? And you can make arguments for the others as well, for every other stroke. Similar arguments. So that's how you could describe the pattern. We found the fastest swimmer for each of 3 of the strokes, and the 4th swimmer swam more or less just what was left. Okay? That's how we minimized swim time for the relay team. We could do optimization sensitivity. We could ask how slow would Todd have to be at the backstroke before we wouldn't want him swimming that. Or we could ask a different question, like how fast would Carly have to get at freestyle before it's best for her to swim freestyle, right? And so forth. I'm not going to do that tonight. Obviously, using optimization sensitivity like we just did, you could answer questions like that. Okay? All right. Let's do one more example and we'll take a break. Another kind of network optimization. Okay? So, pretty much talking network optimization tonight. We've talked about a transportation model where you're figuring out how much of something to go from some number of sources to some number of destinations. The assignment model is similar. You have what we would call source and destinations, but the key is you're not talking how much. You're either going to allow something or not allow it, or assign something or not assign it. So we're always zeros and ones as our decision variables. A transshipment model is essentially 2 transportation models put together. Okay? So, for example, you have a company that wants to find a minimal cost shipping schedule. So again, we're going to minimize cost. It's going to ship product from 3 factories where the product's made to 2 distribution centers where the products may be packaged and prepared for retail. Okay? And then you have to ship from the distribution centers to warehouses or retail stores, let's say. So there's 2 phases to the shipping. Right? You got to ship from one set of sources to some destinations, and then in the second phase, those destinations are now the sources shipping to a new set of destinations. So here's 2 tables representing those models. So we have our 3 factories. We have 2 distribution centers. We know how much it costs to go on each of those 6 possible routes. Our factories have a known capacity, how much they can make. Okay. Then, from our 2 distribution centers, we have 5 warehouses they could ship to. We know the cost for all those 10 routes. And the warehouses have a requirement that is a minimum or a demand that must be met. So it doesn't matter how much product comes into distribution center 1 in terms of a capacity or a demand, only as long as everything that comes into that distribution center then gets sent out to warehouses. Okay? So there's capacities on the factories, there's requirements on the warehouses, but the distribution centers that sort of sit in between don't have a limited capacity. They just have to say everything that comes in must go out. Okay? So let's visualize that real quick. three factories. We'll say F1, F2, and F3. Okay. F1 has a capacity of 2,500. F2, similarly, 2,500. F3, similarly, 2,500. Okay. They're going to ship to two distribution centers, DC1, DC2. Those distribution centers will ship to 5 warehouses. Okay. The warehouses have requirements. That is, we have so much we want coming into them. In this case, 1,200, 1,300, 1,400, 1,500, and 1,600. Okay. And the key is we want to find how much to flow here in this part and here in this part to meet these capacity constraints, these requirement constraints, and the sort of implicit constraint that everything that comes in must go out. Okay. Technically, maybe you could have more coming in as long as you had equal or less going out, but it would never make sense to ship something that you were just going to hold on to. Right? So everything that comes in to the distribution center must be sent out. Okay? So we have 6 decision variables here and 10 decision variables here. So 16 decision variables total. 3 capacity constraints, 5 requirement constraints, and 2 implicit constraints that say what goes in must come out. Okay. So let's copy this. We'll take it to Excel and solve the problem. So there's one table. There's another table. Okay. Resize some of these so we can see them all easily enough. All right. So let's start with our decisions. So we have 6 decisions to make initially for shipping from factories to distribution centers. All right. So I don't know what those will be. We'll start with a guess of 0. Then we have another 10 decision variables, 10 decisions to make that say how much comes out of each distribution center to the 5 different warehouses. Okay. We can sum each row in the first phase to know how much product is shipped out of each factory, such that we can limit those to the capacities. We can sum each column of the second phase to know how much comes into each warehouse, such that we can constrain that to be meeting the requirement. However, we also have to sum the other things, right? The columns of the first and the rows of the second, because those are going to have to be constrained to be equal to one another, right? So everything that comes in to distribution center 1, represented in this column, must equal everything that goes out from distribution center 1, which is the row of the second phase. Okay? So decision variables, we're going to break it into 2 phases, just like we have our parameters broken into 2 phases. We'll create our constraints, sort of like we did before. And then finally, we need our objective function. So our objective function is the costs in phase 1 multiplied by the decisions made for phase 1. Okay. So I'll call that factory to distribution center. I'll separately compute the sum product of the costs to ship from distribution centers to warehouses and how much we decide to ship. and then I'll just sum those two things together, okay, for the final objective. You could compute that in a single cell if you wanted to. Might be useful to see the difference, to see how much we spend shipping out of factories and how much we spend shipping into warehouses. It's two different numbers. All right, so we'll limit these. So let's start with decision variables. We have 6 decision variables here. We have 10 decision variables here. You can enter those separately, and what you'll see on the model tab is there's 2 sets of normal variables under optimization. So 2 sets of rows, columns, cells. Make our constraint. So our constraint on capacity say you must ship no more than, so less than or equal to, the capacity. The requirements at the warehouses say you must ship no less than or equal to, we'll just use equal to, the requirement. And then we have to set a constraint that says what comes into distribution centers must be equal to, strictly equal to, what goes out. Okay? Otherwise, right, if we didn't do that, it might find, well, I can ship from factory 1 to distribution center 1 very cheaply, right? So maybe I ship everything to distribution center 1 for factory 1, so distribution center has nothing shipped to it, but in phase 2, I try to ship things out of it to warehouses because it's cheaper that way, right? Obviously, if it doesn't have any product coming into it, distribution center 2 can't ship product out. So we have to limit and constrain those things. And then finally, our objective that we'll minimize. Again, we need to assume non-negative, same reasons as before. You don't want it trying to ship negative amounts to save money. So let's solve. And the solution looks like this. So the minimal cost is something like $12,881. We ship all of factory 1 product to distribution center 1, all of factory 3 to distribution center 2. Factory 2 ships a little bit to both. Okay. Furthermore, each warehouse gets all of its requirement from one distribution center only. Okay. So it turned out, if you remember back to the first model we did with transportation, there were some cases where you would ship everything from one source to a single destination. There were some cases where a source had to ship to multiple destinations. Similarly, there were some cases where a destination got everything from a single source. There were some cases where a destination got something from multiple sources. Okay? It turns out in this model, in the second phase, there's no double shipping to a warehouse. That is, every warehouse gets everything it needs from one and only one distribution center. It's the first phase where we have to figure out a way to balance things out, right, and ship a little bit to 2 warehouses or 2 distribution centers from the same factory. It won't always come out that way. It probably just turns out that costs in distribution center shipping, or the difference in cost in distribution center shipping from factories, is less than the difference between cost of shipping to 2 warehouses. Okay, so you could describe this pattern like I did. Shipping everything from factory 1 to distribution center 1, factory 3 to distribution center 2, factory 2 to both, and every warehouse gets everything from one distribution center. 1, 3, 5 get from distribution center 1, 2 and 4 from distribution center 2. Okay? We could visualize that. Easy enough. All right. Okay. And we could label those. So we know everything gets shipped there. We know everything gets shipped there. Oh, I'm sorry, not everything does. Only 2,000. And we know factory 2 sends more to distribution center 1, less to distribution center 2. And here, it's easy enough. Every requirement's met from one distribution center. So it's simply 1,200, 1,300, 1400, 1500, 1600. Right? So we had 16 possible routes. We only used 9 of them. 4 in phase 1, 4 of the 6 in phase 1, 5 of the 10 in phase 2. Does that make sense? On the homework assignment, right, I would expect you to build models like this. I would expect you to answer the basic questions like what's the minimum cost or what's the optimal objective. I would expect you to answer questions like what's the pattern of the optimal solution. So what decision variable values were chosen, right? Everything from one place or not another or something split or whatever, okay? Many ways you could describe that. I would ask you questions like how many of the shipping routes actually got used. In this case, 9 of the 16, okay? And I might ask you things about optimization sensitivity. So, for example, you might say, well, since distribution center, or since warehouse 1 gets all of its product from distribution center 1, how expensive would that route have to be before you wouldn't do that? Or you could say, how inexpensive would the route from distribution center 2 to warehouse 1 have to be? How cheap would that have to get before we would prefer shipping from distribution center 2 to warehouse 1 as opposed to distribution center 1? Okay? So optimization sensitivity to change one parameter of the model, okay, and find where the pattern of the optimal solution changes in some way. Okay. All right. Yes, question?
So with these, I mean, it'd kind of be the same as what we've done before as far as like the amount of decision variables and constraints, or I guess the limiting constraints on those numbers. What will one be here of the binding constraints?
Oh, okay. So what are the binding constraints, right? The binding constraints in network models are pretty much always going to be, right, your capacities or your demands or requirements. So in this case, we had to meet every requirement. Those were binding constraints, right? We could have got a better cost by shipping less to the warehouses, but we couldn't. There was a minimum. We had to meet it. That's a binding constraint. In this case, 2 of the capacities were binding and 1 was not. That is, we shipped everything factory 1 and 2 had, and not quite everything that factory 3 had. Right? So 2 of those capacities were binding, 1 was not. So in this case, there's not constraints. There's not as many constraints as there are decision variables, if that makes sense. That's balanced by some of our decision variables we chose 0 for, right? We just chose not to use them. It wouldn't have mattered, right, if we were allowed to ship from factory 1 to distribution center 2. We could have disallowed that. This pattern would still hold because we chose not to use it anyway, if that makes sense. And then, obviously, not a constraint, but since we're minimizing the objective, right, we had to choose things to minimize that. So that also drove the decisions. But in terms of binding constraints, yes, there are some. The requirements, in this case, some capacities. And I guess, you could call the constraint that everything that goes into distribution center 1 has to be what goes out. That's binding, right? We made that. We didn't give the model an option of whether that should be binding or not. We said it has to be equal, right? You have to do this. Otherwise, you're bending space-time or something, right? You can't do that. So those technically were binding constraints. I typically don't ask about binding constraints with network models like this one, just because they're almost always implied. You have to meet the requirements. Sometimes your requirements, the sum of your requirements exactly equal your capacities, and in that case, all the capacities are binding too. In this case, they don't, so obviously you don't want to meet them because that means you're shipping more than you have to. So you wouldn't want to do that. So typically I don't ask about binding constraints just with network models, just because they're not as important and not as telling. Yeah. Good question though. Okay. So that covers transshipment models. We're going to kind of move into a more advanced kind of network model. First, we'll take a break. Okay, so let that soak in for a few minutes, and then we'll move on to something a little more complex, in which everything that flows into something doesn't necessarily have to equal everything that flows out. Okay, so that's where we're going to relax a constraint or change a constraint to say maybe everything that flows in, some of it gets wasted, and it can't all flow out. Some of it, gets trashed or wasted or lost, or conversely, maybe more goes out than can come in. Maybe something produces more; it has interest that it produces, or something, such that more goes out than you put in. Okay, those kinds of network models we'll cover in the next section. So we'll take a 15-minute break, or roughly 15-minute, and begin again at 8.